So when we talk about analog and digital computing, there's a lot of different questions a lot of different questions around this. And one of the first questions is, why on earth would I bother? We have so much infrastructure with digital built up over so many years. And if I think about it, I've got everything is programmable. We have multiple levels. We have so many different layers of understanding, code upon code. Why on earth would I want to mess with this, right? And part of the question is, well, what is a possibility in digital? What is a possibility in an analog space or other related physical computing structures? And then, how do I begin to start to at least motivate this approach? Because it's a fairly good question. There's so much done in digital. Why bother? Well, it actually was the first time that I basically got written carefully after people started seriously rethinking analog again after digital had gone through its revolution, was discussion that came from Carver Mead in 1990. So the same Carver Mead who actually was one of the two key people who created the digital VLSI revolution. It was Carver Mead and Lynn Conway, two amazing people who sort of pushed against what was the common thread at the time and kind of common viewpoint at the time that, yeah, you really never could abstract digital and never could make all this work. We take this for granted now. That was certainly not the viewpoint at the time. And so that same Carver Mead kind of said, okay, well, now let's see what else we can do, right? And was a lot of different questions on neuromorphic and other kinds of, and analog and other sort of things of using as much of the computing of the transistor. So you ask the question, all right, so why would analog be better than digital? And basically the hypothesis and the way he talked about this was, if I have to do a multiplication in digital, I need to have many transistors switch for a particular multiplication on average to be computed. And whereas in analog, to actually compute a multiplication, I would only need, not only would I need to only have one or two transistors, but they wouldn't have to move the full power supply either, because I'm encoding things in between the voltage rails over some range. So he hypothesized that you should see thousands of improvement in energy efficiency, which means basically the amount of energy you would require for a certain amount of computations. So it kind of normalizes the speed question, the speed power question. Also would say that the size would be a lot smaller as a result. And so this was a really important hypothesis in 1990. This eventually became proven undisputably with the vector matrix multiplication measurements in 2004 at CICC, certainly with some earlier senses of this from other things that had been built, but it sort of was firmly settled at that point. And so this became a way of kind of asking some questions of, so what is a factor of 1,000? Carver probably said a few more than a factor of 1,000, but thousands, and we'll work from there. What does a factor of 1,000 mean? Well, if you go from, at the time, and this is sort of held up from when was the first digital signal processing chips, to their energy efficiency, sort of where things flatlining out, that's about a factor of 1,000, and that's an amazing shift for those who might have had an opportunity to live through computing from, say, say 1980 to 2010. It was unbelievable how much things just kept improving. It was like Murphy's law was just not valid in at least in a perceptible case from what you would see as a consumer. So it was pretty incredible. Sort of I'm borrowing a little bit on how Carver would talk about it directly, how Carver Mead would talk about this. Well, a factor of 1,000 means that an analog VMM is kind of at the geometric, means that where we were digitally was at the geometric midpoint. There's a whole additional amount of opportunities in front of us that's equally great. And that's actually a pretty cool that's a pretty cool thing to visualize, of how much things changed from 1980 to 2010 to where they could go from the time when we start looking at these questions, say in 2019, to say 2050. But maybe it won't take that long, no idea, but that's the amount of opportunity, and could kind of see that scale with new capabilities. Okay, so one of the questions always comes down to is, well, how do we know what actually happened on the digital side? And this is actually one of the earlier plots, or some actually updated plots that were created by this. But basically what we ended up finding was, if you started looking at commercial yielding chips, that the energy efficiency for a certain size 32-bit multiply accumulate, before 2004, just went along traditional Kumi's law, Mead's law, all sorts of different scaling laws, all the same concept for the last, multiple decades. Exactly what you would expect as you scale the devices. And yet it started to change. And there's multiple interesting anecdotal stories around this. But basically what you started to find is that the computing part didn't get any better in actual yielding chips. Maybe one-off you could maybe do something better, but nothing in the yielding structures. Something that would yield. And what you end up finding out of this is it seems like it's the mismatch in the digital pathways, and having to compensate for that really sort of constrained what you could build. And this turned out to be a really, really, really big constraint, because basically it said that in terms of energy efficiency, you really didn't improve significantly a lot from a 130 nanometer, down all the way, down to 32 or 28 nanometers. There are some slight improvements at 22 when you went to FinFETs, because the mismatch was actually better controlled, so you had a one step improvement. But in general, it really hasn't improved that much. And this is kind of surprises people how much this has been a typical effect. And so we talk about energy efficiency. Well, right at about 10, basically 10 GMAC per second per watt is basically the number you see. I'm going to use MAC as multiply accumulate, and so GMAC could be billions of multiply accumulates. What's interesting about that is that kind of sets where the wall is. You can imagine where the analog computing is, and you see a lot of things in this region. For those who are kind of curious of how much further this goes, well, biological neurons are actually a whole lot lower, at least to the best guess we have today of what the computing does. And I'm just thinking of just in the electrostatics and the chemical side of it. Just of what we know, the numbers are already looking a lot lower. So that's another 100,000 improvement. So that's pretty interesting, pretty exciting. And if you're really enthusiastic about things like what is the possibility of neuromorphic computing, it is the case of saying, let me take what is a starting physical algorithm in analog space, and I can get even better energy efficiency for a range of applications and a range of algorithms that actually can have some huge impact. There's actually been some experimental concepts that have shown some of these energy efficiencies, and I think there's some of which can actually, by shrinking and scaling transistor sizes, will help. There's a huge opportunity in front of us. And this is just talking about the analog and the neuromorphic side. There can be so many more things that we just haven't begun to see. And it's not doing anything about the question of computational complexity. It is simply a question of this just operational efficiency. So there's so much there, and I like to think of this graph really connected, because right now we usually see from about here to here, and wonder, my gosh, maybe we're almost, we've hit a wall. We're not going to go any further. And in practice, I think that it's quite different. And to kind of echo the words from Feynman in '59, there's so much more room below us. There's so much more room to go. I don't even think we've begun to imagine where this can go. Other than that, we have seen what huge scaling could do. So now one can say, okay, how do we get there? And there begins to be at least some roadmaps of how we might achieve these opportunities.